Hey everybody. So we've been doing a lot of work thinking about limits and what they mean intuitively, looking at graphs and tables, but we can't always count on graphs and tables to help us out. It's not always easy to read exactly what it looks like something's going to, and we certainly run into problems where our technology can fail us. So we want to have a set of rules that we can use to compute these limits algebraically. We're not going to prove these rules, but we'll try to at least get an intuitive sense of why these rules might be true, and then we'll be free to use them moving forward. So we're going to develop what we call the limit laws. So we're going to let's put a couple symbols out here. I need some real numbers, so I'm going to have real numbers A and C. So I'm using some math notation you might not have seen before. This just says let the symbols A and C be members of, that's that little backwards E or curvy E, be members of the set of real numbers. That's the big R. So A and C are symbols that just represent any real number. We'll also have two functions, f of x and g of x, are functions defined near A. So near means on an open interval. Let's put that in here. On an open interval containing A. Okay, but I'll often use the word near, and that's what I mean. Let f and g be defined near A, so some open interval containing A, except possibly at A. Right, so again, we're dealing with limits. We don't care what happens at A. So it could be the case that the functions are not defined at A. And we will assume the limit as x goes to A of f of x is known to be L. The limit as x goes to A of g of x is known to be M, where L and M are in the set of real numbers. There's that set of symbols again. Okay, so that's all our setup, all the stuff we're going to be taking limits of. So let's start with some pretty straightforward limits. Suppose I take the limit as x goes to A of the number C. This is just saying, so remember, we take a limit of a function, and when we take the limit of a function, we're saying the function gets closer and closer to this value if I choose x closer and closer to this other value, right? Well, the function here is just a constant number, right? If the function is f of x equals 7, changing the input of x, right? If I'm taking the limit as x goes to 1, changing the input x doesn't change anything about the output. It's always at C. There's no other number it ever gets closer to, and it's always infinitely close to C. It is C. So changing x has no effect on the constant. Here's another straightforward one. What if my function is just x, the limit as x goes to get to A of x? Another way we could state this is, as x gets closer and closer to A, what does x get closer and closer to? Well, that's A, right? As x gets closer to A, x gets closer to A. It's self-evident. All right, let's get a little more interesting. If I take the limit as x goes to A of the sum or difference of two functions, this is equivalent to taking each limit individually and adding them together, right? In this case, that's L and M, the two limits that we have of these functions, right? So if f is getting closer to L and g is getting closer to m, when we add those two functions together, their values must be getting closer to the sum or the difference of those two values as x gets closer to a. And we'll do some examples of all of these in just a couple minutes when I finish listing all the rules. If we have a function times a constant multiple, remember c is a number. If we're taking the limit of a constant times a function, taking the limit as x goes to a of a constant times a function, this is the same as taking the limit of that function and then multiplying it by that constant, right? So if f is getting closer and closer to the number 7 as x gets closer and closer to a, but we're taking f and multiplying it by 2, then the outputs are going to be getting closer and closer to not 7, but 7 times 2 or 14. So symbolically, we see that the constants can slide through outside the limit. What's next? We've got product rule. So the limit of f of x times g of x, similar to the sum rule, we can take the limit as x goes to a of f of x, multiply it by the limit as x goes to a of g of x, or L times m. All right, so if f is getting close to L, g is getting close to m, when we're multiplying those two things together, they're getting closer and closer to the product of L times m. Similar thing, if we're dividing them, we can take, if we're taking the limit of a quotient, it's the same as the quotient of limits, provided that limit for g is not 0. If the limit for g is 0, then we have to work through these other ways, and we're going to learn some other techniques. These laws are going to be our beginning techniques. Okay, we've got a couple more. We've got the power law. Actually, I don't want to name them because they're not standardized names. I'm just going to do the symbols. Limit as x goes to a of a function taken to a power. We can take the limit first and then use the exponents. And then we could also write that as L to the n. This is where n is equal to the positive integers. Some texts use the symbol as capital N, some include 0 in that, so it's not that's not standard. Let's do one more. We've got a similar thing for roots. The limit as x goes to a of f of x 1 over n is the same as taking the limit as x goes to a of f of x and then taking the root. This works same thing and is a positive integer. If the limit is less than 0, this only works if n, let's say it this way, if n is even, assume L is positive. If n is even, assume L is greater than 0. Right, if L is negative and we're taking a root, a square root or a fourth root, then we're going to end up with complex numbers, which we're not dealing with. Oh, I could include 0 here. Okay. All right, so there's our first set of rules for actually computing with these computing limit laws. Let's do some examples. Okay, so let's do a couple of simple examples with those first couple rules. The limit as x goes to 2 of the number 7, right? Making the variable x closer and closer to 2, what does that do to the number 7? It does nothing. right? Or another way to say that is I can make 7 as close as I want to 7 by taking x close to 2, which is true. If I make x any value near 2, and in this case, near can be infinitely far away, which is a strange thing to say. 7 is still 7, right? It's still close to 7. Another straightforward example, the limit as x goes to 2 of the function x is just 2. Okay. So let's start building up some more complicated things we can do with this. So let's look at, I'm going to use that constant multiple rule. If I take, and what we've done here, if I take the limit as x goes to 3 of 5x, I'm going to combine some rules here. I know from this rule about constant multiples that I can slide that 5 outside. All right, that's what that rule tells me. If I have a function times a constant, here I have the function x times the constant 5, I can slide that function out. Now I can apply the rule we just did above. I know the limit as x goes to 3 of x is just 3. And now I have that limit is 15. Okay. Let's add some complication to this. The limit as x goes to 3, let's make it 5x squared. Well, I can slide that 5 out again using the same rule as before. I can now also use this rule for powers and say, oops, let's go back to black. I've still got that 5 out front. Now, instead of taking x squared, trying to figure out the limit of it, I can take the limit of just x, which I know how to do, right? We've done that above, and then square it afterwards. So I got 5 times 3 squared, or 5 times 9 is 45. Okay. Let's do one more example here, and then we'll do a bigger example that clarifies what I'm heading for here. The limit as x goes to 3 of 5x squared plus, let's do 2x. Well, now I can use that sum rule and decide to evaluate it this way. Limit as x goes to 3 of 5x squared plus the limit as x goes to 3 of 2x. Well, we just did the limit of 5x squared as x goes to 3. We just did that above, so that work's not going to change. We still have a 45 there. We can slide that 2 out front using that constant multiple rule, and we've got an x. The limit as x goes to 3 of x is just 3. We get 45 plus 6, or 51. You might notice something here. Let's do one last example, and then let's make this the limit as x goes to 3 of 5x squared plus 2x minus 5. So now I can apply that sum and difference rule. So you get this. And we just did this one is 45. We just did this one is 6. And we know the limit of a constant is just 5. So we end up with 46. Notice if this was a function, f of x is equal to 5x squared plus 2x minus 5, then f of 3 is 5 times 3 squared plus 2 times 3 minus 5 is equal to 46. Right? The limit was just the evaluation of the function there. This turns out to always be true for every polynomial, right? Every single thing we did up here, all of our applications of these limit laws, we can do for any polynomial. let's do this really abstractly. Let's take P of X to be a general polynomial. So let's say P of X is a sub n, x to the n, a to the n minus 1, x to the n minus 1, all the way down to a sub 1 x plus a naught, right? Here, each of these a sub I, each of these indexed constants are just real numbers. If I take the limit as x goes to some number, shouldn't have used a, well, let's just call it b. The limit as x goes to b of P of X. This is going to be a little bit tedious, but we're only going to have to do this once just to prove to ourselves this rule makes sense in general. We'll have the limit as x goes to b. Let's cheat a little bit here. Whoops, I don't need all that. So there's my polynomial. I'm taking that limit. I can use the sum rule. Take each of these individually. X goes to b, a naught. I can slide each of these constants out front. Oops, I forgot to slide it out there. I can slide the constants out front. A sub n minus 1, limit as x goes to b. Oh my gosh. X to the n minus 1 plus dot 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 a sub 1 limit as x goes to b x. And then this one, we know the limit. The limit of this constant is just a naught. For each of these terms with a power, we can take the limit first and then apply the power. I should have said here, n is going to be a positive integer. It's polynomial, so we can assume that, but I should have stated it clearly. This one, we know how to take this limit. We've got our a1 sitting here. The limit as x goes to b of x is just b. So I get a1 b plus a naught. Now, finally, the limit of each of these x's is just goes to b, and we're left with, oops, not x, it should be b. B to the n minus 1. But this is just the polynomial evaluated at b. Okay, so this is our rule. This is our rule now. So I did a whole bunch of work, and I know that probably got a little bit tedious in there, right? I started out looking at constants, then the identity function x just equals x, or the function just equals x, multiplied by constants, built up all this structure to get to polynomials. We don't have to do that every time. From now on, we can apply, we could call it a theorem, but maybe we'll just call it a rule. If f of x is a polynomial, then the limit as x goes to a of f of x is just the value of the polynomial at a. So that's the only thing we have to do from now on if we want to take the limit of a polynomial, is we evaluate it at the place we're taking the limit up to. What did I say? Forget how I constructed that sentence. In any event, if we're taking the limit as x goes to a of a polynomial, the limit is just the polynomial's value at a. So it's a very straightforward computation. Let's add one last piece in this video before we get to some more complicated examples. Suppose f of x and g of x are polynomials. If we want to compute the limit as x goes to a of f of x over g of x, well, we have that quotient rule for limits right here. We just simply take the quotient of the limits. So we'll have the limit as x goes to a of f of x, the limit as x goes to a of g of x. These are both polynomials. So what does that mean we do? That means we can simply evaluate them. All right. With the small caveat, remember from that rule, we need to know that the limit in the denominator is not 0. So as this holds, as long as g of b is not equal to 0. So for example, if I take the limit as x goes to 2 of x squared minus 1 over x minus 1, I can simply take the limit. Well, I can apply this rule and realize it is just the evaluation. These are each polynomials, so I can take 2 squared minus 1 over 2 minus 1, which is 4 minus 1, or 3 over 1, or 3. And so we can do rational functions as long as the denominator function is not equal to 0 at the place we want to do the limit. So for example, if I took the limit as x goes to 1 of x squared minus 1 and tried to apply this rule, I get 0 over 0. This is not defined. More importantly, or more relevant to this, since the limit as x goes to 1 of x minus 1 equals 0, I was never supposed to apply the rule that I just applied, taking the limit of the top and the bottom. We can do this limit. We won't do it now. This kind of limit will be in the next video. So for now, though, we've got a whole bunch of important stuff. We've got these limit laws, right? So these very basic situations, limits of constants, limits of the x function. And then if we have functions we already know the limits of, we can combine them, multiply them, divide them, different things like that, powers as well. And with those in mind, we built up that we can take limits of polynomials and rational functions everywhere they're defined. That's another way to say it, right? So the rational function is defined wherever its denominator is not 0. So everywhere a polynomial and a rational function are defined, we can take their limits. Polynomials are defined everywhere, so they're good. We're done with polynomials. We only have to evaluate them to take limits. Rational functions, we are only going to have problems at the places they're not defined. And we'll talk about doing that in some of the next videos. All right, that is going to do it. Thanks, everybody. I will see you next time.